Hello students, we're looking at inverses today. I wonder what an inverse is. And let's play around with that idea a little bit. Let's say that we have a set A here that's made up of ordered pairs, maybe 1, 2, and then the ordered pair 3, 5, and the ordered pair maybe 6, 8. Now watch what I do to make a second set. We'll call it B. I'm going to say 2, 1, 5, 3. It's not a good 5. Let's see. Make a nicer 5 here. And 8, 6. Now if you stand back and look at these ordered pairs and see how they relate to the ones in A, do you notice that I've simply switched the X's and the Y's? All right, we would say then that B is an inverse of A, and we denote it by A inverse. We've simply switched X's and Y's. Now we'll come back to that in just a minute, but I want you to think with me. What if we were going hiking and we wanted to get on our socks and shoes? Well, first of all, we would put on our socks, and then second, we would put on our boots, right? In that order in particular. So we come back from our hike now, and we're ready to get into some comfortable house shoes. So I take off the boots, and then I take off the socks. Did you notice I did the opposite action and also in the opposite order? So when we've got more than one thing going on in a relation, we have to think of opposite action and opposite order both when we think of inverses. Now let's go back to our problem on the screen and think just a minute. When we look at the definition of inverses, it requires that both functions, or that both A and B, be functions. We know A is a function because none of the x's repeat. I check B, none of the x's repeat. So truly, B is the inverse of A. But let's say I changed B just a little bit. No, I changed A, I think. Let's change A and let's have a 1, 2, and let's have a 3, 2 right here. Is A still a function? Sure, no repeating x's. But now when I change the ordered pair right down here, I get a 2. So I have 2, 3 right here. And notice that now B is not a function because the 2's repeat. So I cannot call it A inverse. It's just a set B that where A has its x's and y's switched. What went wrong? A was a function. Repeating y's caused repeating x's when we got to B. So we not only have to have a function, we have to have a function that's called one-to-one. In other words, no repeating y's. Now if we used a vertical line test to test for function, what do you think we might use to check for one-to-one if we see the graph? Sure, a horizontal line test. So our definition of inverse says that both A and A inverse, or if we have a function f and f inverse, they most have to be functions first of all, and then there's another requirement. The other requirement is this. If you check your definition in your book, you will find that f of g of x has to equal x, and g of f of x has to equal x if f and g are functions that are inverses. And a lot of times, as we did a few minutes ago, we might say G is F inverse and use the inverse notation. Okay, so what is the requirement for inverses? First of all, F and F inverse are both functions. Second, F of F inverse and F inverse of F both equal x for all x that we're using. All right, let's go forward and see what we might get to so far as problems are concerned. If we have f of x is 2x and g of x is x over 2, we are going to find f of g of x and g of f of x to determine whether the pair of functions f and g are inverses. The fact that they've given us function notation implies that f and g are functions, so it passes that test. So the second test is to find that f of g of x and g of f of x both are truly x, and that's how we'll know we really have inverses. Okay, let's see here. F of g of x. All right, let's see. G of x is x divided by 2. So in place of g, I'm going to put x divided by 2, and then bring over the f and parentheses. Now, f of something here is 2 times the argument, or 2 times the something. And our something this time is x over 2. Well, if I multiply here, the 2's will reduce to 1, and guess what? My f of g of x on the left, coming down every step, does equal x. So it's past the first part right here. Well, let's look at the second part. G of f of x. So we have g of, and our f of x here is 2x. So let's put in 2x. Well, what does g do to something? G takes something and divides it by 2. Our something, or our argument, is 2x. 2 divided by 2 reduces to 1 divided by 1. And sure enough, our g of f of x is x. We are to determine whether they are inverses. Since this turned out to be x when we did f of g of x, and g of f of x turned out to be x, we can say they are inverses. All right, we're doing the same thing here with 2 more functions, f of x and g of x. So, by function notation, we assume that these are functions, which is the first requirement. Second of all, we're going to see if f of g of x and g of f of x are both x, because if they are, then we have inverses. So remember, we have to use that definition of inverse. So f of g of x equals f of, and our g of x here is 2 divided by x plus 3. Well, what does f do to something? It says 2 over our something minus 3. And our something in this case is the 2 over x plus 3. So 2 divided by x plus 3. Let's go up here with it. We have 2 divided by, now there's nothing in front of these parentheses to change anything. So let's pretend they're not there, and we can add 3 and minus 3 and have 2 divided by x in our main denominator. So now f of g of x is 2 divided by 2 over x. Now we could actually write that out, 2 divided by 2 over x, or we could do what we do a lot of times. we could multiply numerator and denominator by the least common denominator of both fractions, which would be x. And since we're using fractions, let's write our x as x divided by 1 in numerator and denominator. Remember, right here, we're just multiplying by 1, so that's legal. We're not trying to do the same thing to both sides. We're trying to doctor up this fraction by multiplying it by 1. Well, multiplying numerators, I get 2x divided by 1, so I don't show the 1. Multiplying denominators, I get 2x, and then multiplying the secondary denominators, I get x. So multiplying secondary numerator, secondary denominator, I get 2x divided by x. Well, that reduces to 1. So I have 2x divided by 2. Guess what? Those reduce to x. So our f of g of x that we started with and worked only on the right side turns out to be x on the right side. So it passes the first test, f of g of x. Next, it's got to pass the test of g of f of x. So let's get us a blank slide here to work with. And work on g of f of x. Let's copy down our f of x and g of x, so we'll have them. And g of x equals 2 divided by x plus 3. And we're working on g of f of x now. So we have g of, and our f of x here is 2 divided by x minus 3. Our g looks like this. So in place of g, we'll put 2 divided by something and then a plus 3. Our something is the argument here, 2 divided by x minus 3. This looks worse, doesn't it? Well, let's see what we're going to do. What if we work on this fraction right here? Now think a minute. I'm not trying to do something to both sides. I'm trying to work on a fraction. So let's do what we did a few minutes ago. Let's multiply by the least common denominator of the numerator and main denominator. Okay, so when I multiply in the main numerator, I get 2 times the quantity x minus 3. When I multiply in the main denominator, the x minus 3's divide out, and I have a 2. Bring down my plus 3 that I haven't used. 2 divided by 2 is 1, and I have x minus 3 plus 3, which is x. So my g of f of x on the left, which never changed, equals x when I work down f of g of f of x. So it passed the second test. I found that f of g of x was x. I found that g of f of x was x. So I know they are inverses. Okay, let's take a break and come back later.